All right, let's go ahead and get started. And so a couple of reminders and announcements. So I'm still looking for more volunteers for the science fair. You're volunteering? I'm putting you guys down. And so volunteers. So volunteer if you can. Otherwise, just share the event with all your friends and family. So I'll post a poster on Blackboard. But so I was talking to some people, and so I had wanted to meet on Friday with volunteers to just kind of touch base. But people were telling me that maybe Monday afternoon would be better. I think Friday is crazy. Does that work for you, Christine, Camilla, and anybody else? Phoenix? All right. So Monday afternoon, I'm thinking like 2 p.m. tentatively. Does that sound good? All right. So I'll send probably a calendar invite. And you don't have to come to this meeting. If you still want to volunteer, we could definitely use people. So sign up, and again, there will be extra credit, 10 points, until I'm trying to bribe you guys. All right. Any other announcements? So, oh.
Do the sources have to be from ACS?
No, they do not. So let's talk about the paper, since I do have the guidelines. And so no, the sources don't have to be from ACS or anything. So any journal is good. So I wouldn't use. So I wouldn't use Wikipedia or anything as a primary source. Oh. Oh. And so again, the idea of the paper is we want to pick our research topic. And so where we're going with this is, so third quarter, I'm planning for us to do like a research kind of symposium, and we'll make a nice poster and kind of summarize everything that you wrote in your research paper onto a nice pretty poster, kind of like you would do, if you were presenting your research. And so I broke it up into smaller tasks. Sorry. Oh my gosh. And so if you look, so on the back, so your paper is due by March 17th on whatever topic. And then this is just kind of a suggestion on how to structure your paper. You don't have to be married to this format. So I'm just letting you know, as long as, it's 5 pages, it's detailed, it goes into something about, the research methods. So it kind of depends on your topic. And then again, you're not limited to these. So I would like it to be somewhat chemistry related, right? But you could still do like biochemistry, that's still pretty chemistry related. People always like drugs as a topic. That's kind of been popular in the past, like nootropics. But yeah, it's not limited, so you can look at any professional journal or textbooks would be good references. And then, so to kind of keep us on track, the first assignment that you have, and it's on the back, is just a rough draft and an outline maybe, and then 2 sources. So that's due by February 16th. So you have some time, right, to start thinking about it. Hopefully you've been thinking about it. And then this will be kind of the first check-in. And again, you can, talk to me about your topic early. So I think it mentions that I want you to have a topic picked by the 2nd week. So probably what I'll do is I'll put it on next week's quiz, just like what topic are you thinking of, and that'll be like a freebie question. And again, you don't have to be married to the topic, but I just want to see that you're going that way, what you're thinking of, and then I can also write suggestions like, if this is a good topic or maybe kind of what to focus on. And then this is what this first check-in is, what sources do you have? Because once you start diving into the topic, it might end up being more complicated than you initially thought, and you might want to just focus on a certain subsection. And then any outlines or rough drafts, anything you can submit by that date just helps you. And again, we're only doing a draft 2nd quarter, so you still have time to rewrite it for 3rd quarter. So I'm not expecting, a perfect paper. I'm probably going to be lenient on the 5 pages this quarter, so if you're a little short, that's okay. We'll make it bigger for spring quarter. And I think, were there any questions?
Is that a final draft needs to be submitted by the 17th or more of a rough draft?
Yeah, so that's sorry, I meant that as like our final rough draft for this quarter is submitted, yeah. And then you'll have your final paper the 3rd quarter, which ideally you'll just be polishing up, what you did this quarter. So trying to give you guys plenty of time to write a nice paper and then turn that into a pretty poster by 3rd quarter. Any other questions on this? All right, so now let's go and we'll continue this chapter. And so we're looking at more isomers. So let's first do a little reminder before we start drawing structures. And so I just want to emphasize what resonance was. So this is just kind of reminders. So remember, resonance is where we're not changing the fundamental connectivity here, but we're just kind of moving around our electrons. So we could see this in our carboxylic acid group, and so it's been deprotonated by some process. And then with resonance, remember it uses that double-headed arrow, and then we're just moving electrons, right? So we're not going to break any bonds. We're not going to like move this oxygen to this other oxygen, right? We're not changing connectivity. We're just moving electrons. So that's mainly going to be in the form of double bonds moving around and other electrons. Oops, I went the wrong way. I apologize for that. And so we can make a double bond with these electrons. And so that could minimize formal charges. But then, of course, we can't have 5 bonds to carbon. So now these electrons move back. And then we can draw, right, our resonance structure. And so again, we're showing resonance, we're showing our electrons moving, and so we're not changing the connectivity. And so now that brings us to isomers. And so now isomers, right, we are changing the connectivity. So does anybody have a definition for isomers? Just kind of a broad definition. What are isomers?
Molecules with the same formula but different structures.
Excellent. So molecules with same formula. But different structure. And I'll put in parentheses connectivity. So, right, that's just saying they're connected to different things in different ways. Right, some could be linear, some could be chains or circles. We don't know. And so now let's look at different kinds of isomers. And so we'll start with structural isomers. And so structural, again, they have completely different connectivity. And so we can compare propanol with isopropanol. And so they are both alcohols with 3 carbons. So of course propanol is our straight chain carbon. So 1, 2, 3. 3 carbons, whoops. So count them, 1, 2, 3. So there's my propanol. And then versus isopropanol. And so this isopropyl group is this. So you might see isopropyl come up. So that's isopropyl. You continue on to OChem, so it's just that forked carbons there. So 1, 2, 3. And then, of course, this is attached to an alcohol here. And so this is rubbing alcohol. And so now let's do a little exercise. And so let's look at hexane. And so the formula for hexane is C6H14. So see if you can come up with the isomers. So what are some isomers of hexane? And then just as a hint, there are 5 unique ones. So let's start putting up at least some isomers. And so we'll see what people get. So who wants to try maybe the first one? So if you go first, you have the easiest shot. I'm going to go, Alira, I saw you. So it'll get harder as we go on, and you'll have to...
I guess I started by making a chain of 6 carbons because I kind of had an idea that if there were a hydrogen attached to 2 sides, I guess 2 sides of the carbon, that would be 12, and then there could be on the end pieces, an extra hydrogen, making the total of hydrogens to 14. And this would also satisfy the formal charge of carbon and the octet rule for carbon and the duet rule for hydrogen. This was the only way I could think of. I did not come up with any alternative isomers. 6.
Yep. So that looks good. So, right, hopefully everybody started off with this, so just our straight chain. And so I drew it in 2 different ways. So you probably want to be comfortable with both ways of drawing it. So you could draw it out, nice and explicitly, like Alira did on the board for us. So you can clearly see, right, all 6 carbons and all 14 hydrogens. And then, I always joke chemists are lazy, so we write everything cryptically. So this is hexane in the straight chain. So every point is a carbon, every vertice is a carbon. So 1, 2, 3, 4, 5, 6. And then organic chemists don't draw in hydrogens explicitly on the carbons. So you just have to know this carbon has 3 hydrogens attached to it to satisfy, like he was saying, right, the octet rule. And then carbon has to have 4 bonds. So all that. All right, so that's one structure. Does somebody else want to put another? Oh, yeah.
Is it looking good so far?
It has 6 carbons, so
Okay.
yeah.
Now, I'm not going to draw out all the hydrogens, but pretend that all these lines are hydrogens. And that should work. Do we see what I'm trying to say here? Is that this should have, wait, I'm missing one. Right there too. That's what I got.
Yeah, I'm just trying to redraw it. So we have our carbon here. So 1, 2, and then kind of 2 carbons. That looks like your structure. Yeah. So this is kind of the shorthand way to draw it, and then we could draw it all out. So carbon, 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 right? This has to have a hydrogen. So hydrogen. So it almost looks like 2 isopropyl groups together. So that looks good. So we have 6 carbons, and then let's count up our hydrogens just for fun. And so we can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So that looks good. And then again, I redrew it up on top there. All right, so that's good. Our second structure. All right. Who else has some ideas? And just for fun, I'm going to write the name on here. So this is 2,3-dimethylbutane. But we'll talk about naming third quarter. We'll get a little taste of organic structures. So you don't need to know this now, but I'm just writing it so you can see it. And well, I might as well tell you where the name comes from. But basically, butane, you find the longest carbon chain. So in this case, it's this one. And then you label them 1, 2, 3, 4. And so they have little methyl groups on there. So that's where the 2, 3 comes from. And then dimethyl, meaning 2 methyls on there. But again, you don't have to stress about the naming right now. I'm just trying to give you a preview. All right, so we have 2 out of the 5. Who else has another idea how to draw different isomers out? Another guess? All right, let's see it. All right, slow down.
Oh, okay.
Okay, so what's going on with this structure? You have a
So,
carbon in the middle.
Carbon are connected.
Let me see if I can draw this. So we have a carbon,
Yes. So
carbon, carbon, carbon. So 1, 2, 3, 4, 5, 6.
and then hydrogens on.
And then hydrogens. So this looks good. So this is one of them. Sorry, I'm slow to translate. And so I'll write it out for everyone in the explicit form. And so now I'll redraw it. So we have 2 carbons, so 1, 2. And then kind of this terp-butyl group thing. And so 1, 2, 3, 4, 5, 6. So these structures are the same. And it's new.
I have a question.
Yeah.
I drew the explicit form, but the initial little like triangle, I have it the other way around as like the points pointing up. Does that matter?
It doesn't, so you're talking about like this pointy upside down like this or something? Yeah, it doesn't matter. So this is where things get tricky and people will sometimes write the same molecule a couple of times, right? Because these are the same. So you're right about that. So you got to be watchful, but that's good. So yeah, there's more than one way to kind of draw this. You're just looking for the same connectivity. And then let me check your other structures. So then what's,
This one, so we got carbon connecting to 3 here, and then this is branching down to the carbons.
I'm just trying to see it. Oh, okay, I see. So you have 1, 2, and then this is branching off. Okay, I think I see it. So 1, 2, 1, 2, and then 1 like that. Yeah, so then I'll redraw it. We have our carbon in the center, carbon, carbon. So that's number 1 there. That looks good. And so that works out 2, 1. All right, and then
This
then
one
we got
is
our
a
last
T-shape.
one is T shape. And I'm just double checking. Yeah, it's not the same as that one. It's not the same as that one, so that looks good. I think that's our last unique one.
I had one more.
One more. I think it must be a duplicate.
I don't think so. It's like Camilla's one, but we moved the carbons to the ends. Oh, actually, you're right. It's a variation of this.
Yeah, so then it'd be that. So I think we should have all of them. So let me finish copying this last one. So that was 3 carbon tails. So 1, 2, 3. And then 1, 2 there. I think I drew that. 1, 2, 3, 4, 5, 6. So that looks good. Excellent. And great job doing those last 3 for us. Did anyone have, so you shouldn't have any other structures, but if you did, right, we could put it on the board and figure out which one it's the same as. And so, you know, again, if you think you have a different structure, right, look at it. Can you rotate it? What else can you do? Sorry, I'm being slow to draw. Carbon, carbon. So now you can see why organic chemists just use the little sticks, huh? All right, so it takes forever to draw it out explicitly. So that looks good, and again, right, you could have drawn this backwards. We'll say, right, this is the same, so they're all the same. So just watch that. Excellent job on that. Any other questions? We could go through the names of them. So this is just N-hexane. So that's just our straight chain hexane. So again, it's just based on the longest chain. And then, if we're looking at this one, so again, same thing. All you do is you find your longest chain. So in this case, 1, 2, 3, 4. So it's going to be another butane one. And then you want to give the methyls higher priorities, so you label it 1, 2, 3, 4. So this is 2, 2. And then these were methyls, right? So dimethyl butane. This last one, so you find your longest chain, so that's the 5. And then it doesn't matter which way you write it, so 1, 2, 3, 1, 2, 3, priority is the same. So either way, you get 3-methylpentane.
Would it be 5? Where are we getting 3?
Oh, the 3 refers to where the methyl group is, because you have your pentane chain, and then it says 3 methyl, so after you draw your pentane, it's saying put a methyl on the 3 position. Yeah. And then the last one here, so same thing, find the longest chain. So it doesn't matter, it could be 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, right? Same answer. And then we want to give methyl group the higher number, so that's 1, 2, and this one ends up being 2-methylpentane. Saying that you have a methyl group hanging off of your second carbon there. But again, we'll really focus on naming third quarter. I just wanted to give you a preview and have that there. All right, so now let's look at stereoisomers. And if you've been in lab, you have a little bit of an advantage. So what's a stereoisomer? It has a more specific definition. So what makes it different? Stereoisomers. What's a stereoisomer? flip could be a way to call it. It was, you wanna,
Don't they have kind of the same structure, but yet their geometry is kind of a little different?
so mirrored, I was just looking for like a broader definition, so probably like different spatial or 3D arrangement is what we're going for. But I think everybody kind of was hitting it, right? So different spatial arrangement. So, right, different 3D arrangement. And then people started bringing up examples, right? So they might be mirror images or flipped or something. So that's usually what we're kind of looking for, although not all-inclusive. Or just different, again, different arrangements. And so let's first look at, well, you know, why do we care? And so let's look at this Wikipedia article. So some of you may have heard of this drug before. And so it was initially used as some sort of anti-nausea medication. So you can read it here in the article that first they thought it was safe. And so it was prescribed for people in the 50s and 60s as morning sickness treatment. And then around this time, right, they noticed infants had a bunch of birth defects. And so they later realized that, so thalidomide, if we look at the structure here, so it has two different enantiomers, or right, two different spatial arrangements. And it's all in the difference of just this nitrogen here. And so now let's look more at the, I thought there was a, yeah, so basically what happened is, so the medicine itself is a racemic mixture of those two enantiomers. And I think even if you have the one enantiomer, once it's processed in your body, then it can become a racemic mixture. And so it mentions here, right, the R enantiomer has the desired effect, while the S enantiomer is toxic. So teratogenic just means that, right, that causes birth defects. So chemicals that are under that are highly toxic. And so, right, they said, so right, they attempted to extract just the one chirality, but then again, once it's in your body, it's able to convert back and forth. And so that's something, you know, that can happen. And so it probably gets deprotonated by a base here. And right, our body is basically acid-base chemistry. And so if you kind of deprotonate it, you can get both enantiomers. And so that's also a good, you know, thing to keep in mind. So I always say, right, either you work for big ag, big pharma, or I guess you're teaching like me. So that's what all my friends did. So either, and so, right, if you want to go on to work for big pharma and design drugs, right, that's something that you have to keep in mind is how does that interact with your body and your body's metabolism, right, from the moment it enters your mouth, right, it starts getting processed by your saliva, goes to your digestive system. What does that do to the molecule? How does it get processed? And obviously, what other side effects could there be? And so this is why it matters, right? So chirality is important.
How would you like estimate that, or you're just like human trials and see what happens?
Well, hopefully not human trials first, but yeah, like in vivo studies with like other animals, or sometimes, so in this case, looking back at thalidomide, and we're going to look at this right now, but basically kind of what the issue is you have a proton here that's probably fairly acidic, so you can pop it off, and if you have a vulnerable proton like that, then you might make the other enantiomer. And so kind of looking at that same idea of flipping the chiral center, so this is an interesting article if you ever want to, you know, get into a philosophical discussion with somebody. And so part of what people have been trying to figure out with chemistry is like, okay, let's just say, you know, we were made from our primordial soup. And so part of the issue, or part of the question is, well, how is life just a single chirality? And so there have been lots of studies done to try to, to try to figure out like how we only have one chirality. Oh man, all right, this is annoying. Let me see if I can pull up the paper, because what I wanted to show, and the issue with all these amino acids, so let's just pull up an amino acid. So amino acids, right, all have this little proton here. And so this proton is susceptible to deprotonation. And so that's part of the experiments that they were running with the chirality is first, like how do you even go back and forth? And so basically, in the presence of a weak base, you can deprotonate this, and then you can either reform that same enantiomer, or it might make the new one. Because once you break the chirality, so once you deprotonate it, now it becomes achiral. And then once it's achiral, once it reforms and gets attacked again by another proton, so reacidified, then it could come in from either side, hence where you could either get the R or L enantiomer. Sorry, I was trying to log into my ACS account. Because I wanted to look at the paper. All right, I'll try to pull it up later. I think I have to get on my other access. But basically, the conclusion of the paper, yeah.
I just have a question about, say, isomers. And so prions, I know they're misfolded proteins. Are they technically an isomer of a normal functioning, or is it a little bit more complicated?
Yeah, it would be more complicated because, once you get into the protein folding, that invokes more like tertiary and quaternary structures. So yeah, it's not just a simple.
Okay.
All right, so I apologize for not having access to the paper, but basically what the paper kind of says is that, maybe how we got to one enantiomer is some sort of selective crystallization. And so this goes back to Le Chatelier's principle, but basically, let's just say one of those enantiomers started crystallizing out, right? And then if it's crystallizing out, it's falling out of solution, and then like you learned last quarter with Le Chatelier's principle, then that can continue to drive your reaction forward. So that's some thought of maybe how we got to one enantiomer, but there's obviously a lot of debate and research, and if you're interested in that sort of thing, that's always a good thing to look at. But I'll try to get the actual paper so you can look at the chemistry and how they did it, but I'll have to pull it up on my other credentials. All right, so let's look at, now let's look at enantiomers for a second. So our enantiomers are just defined as non-superimposable mirror images. And so something is defined as a chiral center just if it has 4 different things attached to it. Right, so I drew my carbon here. It doesn't matter what's there, just as long as they're unique. And sometimes this can get tricky in other structures. It could be involved in like a ring structure, and as long as that ring is asymmetric, you still have a chiral center. And so then the enantiomer, if you were in lab, you kind of practice this, but we can add our mirror here. and then just draw it like it'd be flipped in a mirror. So Y, X, Z, and W. And so right now this would be our mirror image. And then of course if you try to, redraw it and superimpose, oh, I think I drew it wrong, sorry. Apologize. So X, Y, I drew the same structure. So W, so that looks better. So that looks like a mirror image. And then rotate it. And so this is where molecule kits are super useful. And so if you ever want to check the school one out, right, feel free, help yourself. But then if we rotate it, and so I'm just trying to rotate it mentally. So, yeah, the X is fine there. Y, but then if we rotate this one, right, then our W is coming out of the plane of the board and Z is behind. And I can make a molecule kit, or a molecule if we need.
Is this what the textbook refers to as optical isomers?
Yeah, so these
Is
would,
another term?
yeah, so that's the same sort of term. So optical isomers. So just different RS conformations. And so your book, I think, mentions limonene. So limonene is pretty much found in one conformation. So you can, the plus isomer, which I forget if that should be the R conformation, but basically limonene, so if you wanted to, you could take your orange peel, peel it all up, put it in some water, and then you could distill it, and then that'd be kind of a painful experience. But if you do that, you'll isolate a nice little oil, and so that oil is mainly limonene, and so that has, right, the orange flavor. And then there is also the negative isomer, so that would probably be the S conformation, and that has kind of like a turpentine odor, but that would only be a very small amount in the pure orange peel. So pure orange peels are basically almost just limonene. So if you distill it and then you look at it, like in the optical activity, you should get a really pure number for distilling oranges and lemons. And yeah, so limonene, that also gives a lot of other flavors. So again, this always turns into drug the class, but like, again, those like dabs and stuff, those tend to have like limonene, the terpenes. Like if you look, sometimes it even gives like an analysis and it'll mention different terpenoids like turpentine or others. So all these are terpenes. And terpenes just refers to how they were made. So let's just look at terpene. And now apparently it's just about drugs. But terpenes have these general structures of 5, so 1, 2, 3, 4, 5. This double bond can kind of move around, but this is just a part of natural product synthesis. All right, so now let's look at other isomers. And so now this is going to be specifically for octahedral compounds that tend to have this. And so we'll look at several different types of isomers. And so if we look at this molecule, right, so we have our 4 fluorines and then 2 chlorines. And so what do you notice about these fluorines? What can we say? So different spatial relationship. So right, we have one where they're next to each other. And so this chlorine could be anywhere on kind of this middle axis here. And so anytime they're next to one another, this is called a cis isomer. And this would again be when you have two that are different and then the rest are the same. So that gives you a cis isomer. And then if they're across from one another, so the chlorines are directly across, that would make it the trans isomer. And so you might be able to distinguish these electronically, and so it kind of depends. So they would probably have different stretching frequencies, and there could be some sort of interaction too, since these are, again, across from one another, so you'll have different, perhaps slightly different electronic behavior. And so let's look at other examples. So this is for AX2, Y4 molecules. And so now let's look at some organic structures. So we can also have cis and trans in organic chemistry. And so let's draw out two examples. Oh, and these are hydrogens. So hydrogens. So we can have this sort of structure in OChem, right? So it's going to be a planar structure, but then we have, right, our differences in connectivity again. So if we have our chlorines or our same group on the same side, this is called our cis isomer. And then now that our chlorines are across, this would be trans. And so the key here in organic chemistry is that we have a double bond, and so it does not allow for rotation. So, right, we can't just flip between those two isomers. There's no rotational freedom there because of the double bond. So you would have to chemically change it, yeah.
So if you had this example, but like instead of hydrogen you had like, I don't know, just like anything else, then could you still use the cis and trans rule?
Yeah, so they could be like, you know, two methyl groups.
So how do you choose like which, like if they're both two pairs, how do you choose which pair you're looking at to establish if it's cis or trans?
Just if it's like the same pair, right? So you could, I could have,
Because it would be the same either way.
yeah, because it's the same. So if I had switched it to like, you know, even like a methyl or bromine, right? Like we could put a bromine. So this is still cis, yeah.
Okay.
So as long as, whether it's different or the same. So bromine, so this would be our trans still. Excellent. And then, so then if you were playing with lab, then you also ran into this scenario. So this is for our square planar complexes. And they have to have some general form of AX2, Y2, right, where they have two. And this is where we can use the term ligands, right? So these are just ligands, things attached to metals, or we can call them groups, substituent, lots of interchangeable terms. And so now we can have the same sort of scenario. So either the same groups are next to each other, so this would be our cis isomer again, or they could be across, and that would be trans. And again, these would be different electronically. So I assume the easiest way to distinguish them would be by IR, so they probably have different stretching frequencies, but it also just depends like what data you can get and what shows you that you have different structures. so then the last one is back to these octahedral complexes. And so I'm going to draw this a little bit differently. So octahedral, right, normally we draw it, so I'm going to draw this in different orientations. So I could put my cobalt here. And then it's easiest if you kind of like tip it. So notice, right, this is kind of our z-axis, so I can draw it how it's kind of drawn there, or kind of the cheating way is what they did. So, right, you have your chlorine, 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 and then ammonia. And what you're kind of looking for is, can you tip it and then have all these be on a plane? So these are all on a plane, and these are all on a plane. And let's draw this another way. Or, so cobalt, so we want them to be cis, so chlorine, so NH3, and then these coming out, so chlorine, chlorine, and then ammonia, ammonia. So these are all the same drawing. And so anytime you have kind of your, what I call the facial being the same, so this is called your FAC isomer. And so I think your book refers to this as cis-cis isomer, since they're all next to one another, but I normally don't see this term, so usually you see FAC being used. And then if we draw, so now this is our mer isomer. And so let's draw this. And so your book refers to mer as also trans, cis, and you can probably see why, right? So we have chlorines across, we have ammonias across, so these are across from one another. And let's redraw this a little differently. Let me switch pens for our mer. And so if it's our mer isomer, so we can put cobalt in the center, chlorines across, right? So now it's trans. And then one is cis, though, so chlorine. And then that leaves us with the rest of our ammonias. So NH3, NH3, NH3. And then here's our other, right, trans relationship. So we have our two ammonias trans from each other, and then one cis. So there's the mer isomer. Does everyone see that for those isomers? I could also, should have made molecule kits. I was just slow. All right, I'll try to make these isomers. While we look at some stuff. All right, more hybridization, fun. And so let's start off with, let's look at CO, and this might help you with your homework as well. So take a minute or two, and so see if you can draw the Lewis dot structure for CO. And then you might want to start thinking about what kind of orbitals are coming together. What does that look like? And then I'm going to try to make FAC and mer while you do that. So what does your CO look like? It's probably easy enough that y'all can shout at me.
Here's a double bond.
Double bond?
You go triple.
So 2 on each. So I think this is the best structure in terms of trying to minimize formal charges. So we did mention that this was odd, right? So what's the formal charge on these? So this is
+1 on the oxygen, +1 on the carbon.
so +1 and -1. So yes, it is indeed odd, right? So we don't expect that. So usually we want to have the negative formal charge on the most electronegative atom. But again, we mentioned last quarter this was kind of an exception, and this also shows us why CO, when it acts as a ligand, it attaches at the carbon to the metal. But all right, we don't care about that right now. But let's look into, well, how do we get this triple bond? What orbitals go into making this? So what's the hybridization of CO here? Or of our carbon, sorry, in CO. So what do we think? SP? So exactly, so right, it's SP hybridized. And so it still follows along with this, right? So it has one lone pair, one substituent. So yeah, SP hybridized, good. And so now I'm going to redraw this. So my carbon, oxygen. So now I'm going to just make my SP hybridized orbital. So one of those has the lone pairs. Now this is prime for bonding. Maybe I put my oxygen too far in the outer space. And so now looking at our oxygen, so what's our hybridization on our oxygen? So also SP. So SP hybridized as well, good. So now we have, right, our sigma bond. So we can tell we have, well, one of these bonds is our sigma interaction, right, head to head. And so how do we get our triple bond, though? What orbitals go into play? What orbitals are left?
I'm not so sure exactly what axis they're on, but the PX and PY, or maybe PY and Z, or whatever it is.
I like X and Y. So like I said, Z is usually the principal rotation. And so by that convention, that leaves, so we'll call, I guess, PX going up and down. So I'll shade, right, our P orbitals. Now this is PX. And so yes, right, so they both are SP hybridized. So they both have PX orbitals and PY. So let me go ahead, try to draw PY on here. So PY. And so exactly, right? So this is telling us, this is how we got our triple bond then, is we have one pi interaction, right, with our PX orbitals. So we have a pi bond. And then our other pi bond comes from that PY interaction, again, through space, right, just as long as they're in phase. And so now we can say for our CO, we have one sigma and two pi bonds. And again, I don't think your homework asked for this, but for us, right, we want to say, well, you know, we have SP coming together. And so those orbitals are head to head to make our sigma bond. And then our two pi interactions were PX and PY, kind of through space. So excellent. So questions about this so far? Yeah.
Is there a limit on how many bonds that two atoms can have together? Like, is there more than 3 triple bonds? Like, more than a triple bond?
I'm trying to think. I don't think you could have a quadruple bond, but I'm gonna ask Google to see if anybody's like done that research-wise. But yeah, you kind of reach like the limitation of how many orbitals you have, and usually there's other like octet rules and whatnot, why you don't have like 4 bonds. I'm trying to, yeah. So I'll research that question. But let's look at acetone, and so take a minute or so and try to figure out what's my hybridization of all these atoms. So we have our 3 carbons, 1 oxygen. So what's their hybridization? Oh, the 3 there? Sorry. So let's hear what y'all think. So what do we get for the oxygen? And I kind of left off something. So what should I probably add to my oxygen, which would help with your hybridization? Yep, so 2 lone pairs. So I kind of left them off on purpose to see if you'd notice. And so what's our hybridization on oxygen? So sp2. And then what about this central carbon here? So also sp2. And then these carbons are symmetrical, so what are they? So sp3, so sp3 for both of those. And so again, we can do our analysis and just kind of see who goes where, who's bonded to who, how do we get this double bond. And so you're kind of noticing, and this should help you on your homework, right? So if you have, I'll just write this off to the side. So if you have a single bond, right, that has to be a sigma interaction. So that's the only way, right, you first make a bond, there has to be some sort of head-to-head interaction. But then once you get to a double bond, right, well, we know we still have to have our sigma bond, but then you probably have 1 pi interaction, as we're kind of seeing. And then for our triple bond, right, that means we have to have a sigma and 2 pi. And so right now we're just kind of verifying this, right? So we've kind of seen this, but we really want to get into, yes, these are the orbitals that are interacting. Yes, I see that sigma bond and that pi bond.
Do you ever have 2 atoms with 2 sigma bonds? Like 2 atoms connected by 2 sigma bonds? Like a double bond without sigma?
Yeah, I don't think that would happen at least not that I can think of. The only like thing that maybe is somewhat related is, remember how we've talked about like ammonia and stuff? And so this could be contributing, we would still call it like a single bond, but this is kind of more for later, like if you were to go on. So sometimes people call this a Z bond, a Z-type bond, which just means that your ligand is donating to. But I don't think that you would have like 2 sigma bonds. But again, I can't think of a scenario, but that's what chemistry is about, right? Trying to push the boundaries. And to get back to your quadruple bond, I should have just guessed that metals would be involved. So there are a few weird examples, like this chromium one. They're claiming that this is also a quadruple bond, but I would have to sit down a little more slowly and double verify that. Because Wikipedia was also trying to say that C2 was considered a quadruple bond, but I don't think that that's actually true. But they do exist. But yeah, probably more metal-metal interactions. Not sure about main group double bonds. We'd have to look more into, or quadruple bonds, have to check more into like the literature to see if they've actually been able to make one. But yeah, this general rule will help you. So let's go back to our acetone analysis. So again, right, just drawing out our sp2 hybridized orbitals. And then I'm going to draw my carbon, so oxygen, carbon. And so again, right, we can see they have that sigma head-to-head interaction. And then so if we go back, well, now they both only have 1 p orbital left, right? That's not mixed. So that's kind of the difference. And we could call it px. I'm not really sure what orientation. But right, they both have 2 p orbitals available. And I drew that really jacked up. But right, trying to draw this through space interaction. So again, that's confirming where we got that second bond was from our pi interactions. And so again, right, once you have that double bond, because of the pi interactions, you cannot have rotation. So that's also keys. And so now looking at our little CH3 group, so now sp3 hybridized, and so they're just making our sigma interaction. All other p orbitals are already accounted for, so just giving us our sigma bonds there. And of course we could draw all these, right, attached to hydrogens. It kind of goes on and on. But again, just sigma interactions with those hydrogens. So any single bonds, right, just count them as a sigma bond.
And you would say, like, hydrogen can't be hybridized because it only has 1 orbital.
Yeah. All right, so that looks good. Uh-oh. Sorry, my notes are flying away. So let's look at other. So normally I would have stopped lecture at noon to do our recitation quiz. But your quiz today is just a welcome assignment. And most of you, like, you're just continuing this class, so you'll just tell me, like, I'm continuing the series. So I'll stop probably closer to 12:30-ish, so you still have time to do your really quick welcome assignment. But I just want to make sure we cover all this chapter, so I'm just continuing to yammer on when I would normally stop. All right, so let's look at aromatics as well. So aromatic rings are delocalized pi systems. Delocalized. And so what does this mean? And so let's take a look at benzene. And so first I'll draw benzene shorthand. So right, this is benzene, and so the reason why it's written shorthand is because it's aromatic like this, And so with our delocalized pi system, so we can draw it several ways. And so I could draw the double bonds like this, but again, since it's delocalized, it's aromatic, these double bonds just continually could rotate, so now I'm going to move them to a different position. So right, these are resonance structures, they're the same thing. And so again, that's why you see it like that. And so now we could draw it more explicitly. Let me just draw it once explicitly so we're all on the same page. All right, so we have our 6 carbons for benzene and 6 hydrogens. And so that works out. And so what's our hybridization then of our carbons? Of all these carbons, so that you notice they all have the same hybridization. sp2, right? So they're all sp2 hybridized. All carbons are sp2. And so, right, just thinking about that, so benzene is planar, right? So they're all in the plane, sp2 hybridized, so we could be looking down, right, at a top-down view. But then that means that they have, and we'll just call it, you know, px, so up and down. So this is all available. So now I'll draw out our px's. All right, so each carbon has an empty px, we'll call it, just for formality's sake. Right, so they all have these pi orbitals that are empty, right? And then they're all going to be, we'll say, in phase. So, right, if they're all in phase like this, that is why we say it's a delocalized pi system. So they're all together. So, right, there's pi bonding, pi bonding, pi bonding, pi bonding all throughout the molecule. And so that's what makes it aromatic and special. And so, right, aromatic compounds are often more stable too, so they can stabilize the charge. But again, all that you want to recognize is, yes, they have those px's, and they're all going to be in phase there. Does that make sense for benzene? And so now let's look at some other stuff. And so this is kind of tricky, so I don't know how much we'll test on it in this class, but I at least want to show you it. And because like I wrote our note here. So if you're going on to OChem, look at this, check it out now, right? Be comfortable now, so then when you go into OChem, you won't have heartache and confusion later, which admittedly, I had heartache and confusion in OChem. And so let's look at this so that you're not blind like I am when you get to OChem. And so let's kind of look at nitrogens, because nitrogen can do some funny stuff. And so this is kind of a cheat sheet. And let's just look at this example here, and we'll see what could happen. And so, right, we're looking at this structure, and so it says expected hybridization versus actual. And let's write out those two scenarios so we'll see why it's really sp2, even though, right, it kind of looks like sp3. And so let's draw this out for a second. So we have, right, our nitrogen. And so let's just assume sp3, right? So if you just glance at this nitrogen, well, it's attached to 3 things plus a lone pair. So that's why we might think it's sp3. However, let's draw out those orbitals. And so, right, if we're trying to figure out how they interact, well, we have our oxygen, right? We said this was sp2 previously, right? We saw that in CO, so we could draw that out. So our oxygen is sp2, but then keep in mind, right, it's sp2 hybridized, so it still has what we'll call px hanging out. So same thing, so now our carbon, right, it's also sp2 hybridized. It also has this px hanging out. But now, if this is sp3 hybridized, again, making our wrong assumption, that means, so right, our nitrogen would be here, so it has some sort of bonding orbital, and then our two hydrogens, and then that leaves kind of this lone pair stuck in this sp3 hybridized orbital. But because it's stuck here, right, it's not the same, so it's not what we're calling px, right, so it can't form or do anything with this delocalized system. So what that means, right, is these electrons, because of how we're calling it and its hybridization, it cannot do this. And, right, wrong geometry. They're not set up for that. So, right, we'll say wrong configuration, essentially. So now, if it's really going to behave like this and be able to move those electrons, it actually has to be sp2 hybridized. And so now let's go into actual. So now we're saying, okay, let's try this again with our nitrogen being sp2 hybridized. And so now we can redraw this all. So again, our oxygen was sp2, so its lone pairs hanging out, that's fine. Bonding orbital with our sp2 carbon. So carbon. And again, let's redraw. So we have, right, our what we're calling px, px. So this is all in phase, in phase. And then now if our nitrogen, so okay, let's fix this. So it's sp2. So nitrogen, sp2. So it's making our bond, right? Hydrogen. So these are bonding with hydrogen. Let me redraw that better. So, right, these lobes are primed with hydrogen, so it's in a plane. So now we've changed the geometry too, right? Because this was tetrahedral. So now, okay, hydrogen's back in the plane, sp2 hybridized. And then that means that our lone pair is hanging out instead in this px orbital, right? So now px, right, matches with our carbon. And so now it can donate the electron like we were looking to. So now it's able to do that, right? So correct configuration. And so what I'm trying to show with this mess here, so I'll redraw it. So carbon, right, NH2, those lone pairs. But now that it's in, right, the orbitals match and they're the same orbital, now that it can go, so that's what it's going to do. Those two electrons can go here, right? And again, it can interact with this pi system, and then that just means this double bond will go up to our oxygen, and so that gives us, let me rewrite that. So this gives us our resonance structure of this molecule. So now we have our resonance structure, so this could be relevant in reactivity. We're trying to figure out what it does. But this is a good example of, kind of why it's important to kind of analyze what orbitals do we have, what orbitals are already involved in bonding, what orbitals are left over. And so we see that a lot with nitrogen where it's kind of in these scenarios. So if we look at like this system, so this would be aromatic, right? And that's all because it's sp2. And so if it's sp2, that again means that lone pair is going to be in that px again, and it can be delocalized as well. So if we wanted, we could write this. So it's similar to benzene. So we have our electrons, and then that means that we need our lone pair in what we're calling, right, px, so that it can follow along with this delocalized system, since again our carbons are sp2 there as well. So this would have an empty p orbitals. So now again, delocalization. All right.
So basically, even if these pi orbitals aren't actually involved in any double bonds or anything, they still like to be in phase with each other.
Yeah, exactly.
So even when you look at the Lewis structure and you think, oh no, this must be sp3 because there's not a double bond here, that doesn't necessarily mean that it could be hanging out in just px because it likes to be with that.
Yeah. Yeah, and this is mainly for nitrogen where this happens. And like I said, we probably won't be too involved with this in this class, but you know, especially if you go on to OChem, you want to be thinking this, because this always happens in OChem. And there's a lot of mechanisms that depend on like pi systems in OChem. So yeah, if you can put your nitrogen in the pi system, that's usually kind of favorable. All right, I think that covers this chapter. Yeah, I'm just double checking my notes. So I think that should cover everything. And so you can take a little break if you need, but I'm going to go ahead and hand out the quiz. So like I said, it's just our welcome assignment. So welcome back. And then things that I am looking for is kind of, you know, what worked last quarter, what didn't work, and if I need to change anything, you know, I'm try to be open and flexible to be a better instructor. And then once you finish the mini quiz, you can leave, and then of course we'll have lab at 1 for those. And I lost count. Oh, just pass it. Oh, and then I did make the FAC and MER isomers. So do you want me to just kind of pass those around maybe? I'll just start them so you can look at them.